Yes, I'll get them up. All right, parallel circuits. Let's get into some of the terminology. There is 2 sections for terminology for this quiz, or for this section. So everything still is going to apply. We're just going to get into some more specifics with just the parallel versions. All right, so terminology that we have is troubleshooting. What was that? Constantly. That's one of the things we're training you guys to do, is to become good troubleshooters. There are many different programs throughout the United States, throughout Eastern or Western U.S. and all that kind of stuff. There are some places they do not teach you great troubleshooting. There are some places for lab, which I'm not going to name names, but there are some places that for lab, you're given a little board that has a circuit already prefabricated on it. You put it on a little control board, and then you can measure stuff. There is some options in there, so internally it can do some troubleshooting, but basically what it does is those little trainers that we have on the desk by the computers behind my desk, that's what they use. They're good for some aspects. For testing, that kind of stuff, to make sure everybody gets the same things, they're great. But day-to-day troubleshooting, you guys just building your circuits, we're introducing troubleshooting into that, because how many times does it work the very first time you build it? Hardly ever. So you guys have to troubleshoot to figure out what's wrong with my circuit before you even get to figuring out, did I build my, is this right? Is this close to what I'm measuring? Yeah. Yeah, it's the reason that we do the reason that we do these labs this way is to give you guys troubleshooting experience. Sometimes it can be as simple as you have your leads connected up on separate rows for your connections. You have your resistor and your power on one separate line on your breadboard, not the same. Okay, that's a common issue, and that happens quite often. It's not going to be as a big deal now, but when you start getting into digital, it can be detrimental, because you could put a power onto a ground line, or put more power than what you're supposed to have, and you could fry chips. So it's important now that what you guys are doing this is make sure you pay attention to all the little details. Make sure everything's connected up correctly and properly, and work through it. And the idea behind this is troubleshooting. It's a systematic process of isolating, identifying, and correcting the issues. Okay? That's why we have you guys build them from the ground up, because you can troubleshoot them as you go. And you'll start to pick up on some things. When you get into some group work, we won't have a whole lot of it here. When you're working in teams for the projects, or if you've ever been on a robotics team or things like that, there's going to be times you're going to be troubleshooting somebody else's work. And so you need to have kind of the same systematic approach no matter what your problem is. Okay, where do I need to start? The first things I usually try to look at when I'm troubleshooting is, okay, voltage is easy to measure. It's non-invasive. I don't have to do anything special to it. I can just take my DMM and start probing. Okay? Just about any tool you work on, you can just start probing with a DMM. And the thing is you want to start finding out, do I have my voltages? Because a lot of times, the problems that we had on tools would come back down to simply our power supply was shot. We were supposed to have 5 volts, 12 volts, plus or minus 24 volts, and sometimes 12. And one of those would be gone. And nothing else would work right, because they're relying on those other voltages to be able to rail and do different things. So if we didn't have those voltages, really quickly, we could have spent, going down the nitty-gritty, finding out which component was bad, when really it was a whole system. One power supply was not working correctly. So having some sort of an idea in your mind as you're troubleshooting through these questions is, do I have the voltages in the places that I should have voltages? That's one of the reasons why we have test points. So when you're building circuits, you can you can build in test points and include them in your documentation and your write-up, so the person behind you can go, why isn't this working? Well, let me run through these 6 test points to make sure I have what I'm supposed to have. Those will become in more handy in that kind of idea when we start getting into power supplies, because we're going to break them up into stages, and each of the stages, it's a very predictable thing of what you're supposed to have. And if you don't, then you know where your problem is. Does that make sense? So again, troubleshooting is a systematic process of isolating, identifying, and correcting issues of the circuit. Finding out what's wrong is only half the battle. You then have to correct it. Along with troubleshooting, we have half splitting. This is just a fancy term for a way to troubleshoot. The idea is we take a system. So let's say we have a system or whatever that has 10 contact points. We know this is going to be our input on this pin here, and this pin, let's just say we have an amplifier. Okay, so this is going to slowly step up the amplifier. We're going to get our output, which is going to be, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'll say 9 times the input. Okay, just for examples. So basically what this is going to do is at each stage of this amplifier that we're going to have, it's going to amplify it up so much percent until we get up to where we get all the way up to where it's amplified 9 times. So when we test this guy, let's see, this should be, let's see, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so when we test these guys, whatever voltage we test here to ground is going to give us our baseline. At the out, it should be 9 times larger than whatever it is that we put in. Okay? So in this method, let's say I'm putting in 1 volt, and I should be getting 9 volts out. So what I can do is I can test this guy. So I come up in and I test across my output, knowing that I should be getting 9. Let's say I'm getting 4 volts. Okay, so just like in our lab books, we're calculated to be getting 9 volts out. We measured, and we only got 4 volts. Now, this method of half splitting for troubleshooting is we're going to go back through the system, and we're going to figure out, the most systematic way to approach figuring out where the problem is, because we need to know which subsystem to go tear into, because this could be several resistors, a transistor, a couple other things, capacitors, that kind of stuff. So we need to know there's lots of components. Figure 8 stages of amplification. There's going to be 8 transistors. There's probably going to be close to 32 resistors, probably another 8 or 9 caps. We need to know where to go for the problem. So half splitting is we're going to split our options straight in half, especially in a system that builds upon each other. So we're going to measure from here to here, or measure from here to ground. This is going to be our first measurement. Well, when we measure there, we're getting 4 volts. Is this what we were expecting to get? Yes, because we're on stage 4. So we know that because at this point we've selected this half, we know at this point everything previously is working correctly, because we're getting what we're supposed to be getting. So we can eliminate that portion, that half, as our problem. So now we can go in and we can look at this guy. This one would be pretty easy to kind of take an educated guess what we're getting. Okay? So if we were to measure here, so now that we've split it up our first time, we're going to split it up a second time. So every time we have options, we're going to split them in half and choose one side or the other to look to see if our problem is. So here, if we were to look at 7, we're measuring this, we're getting 4 volts. So we know that we still have the same 4 volts here, so that means this side is not our problem. I mean, it could be, but the problem we're looking at now was caused before this stage. So when we come back, now we have one last time to look at it. We split it again. We split it in half. This is where the half splitting comes in. So we're systematically dissecting this system to find out where is my problem. So at this point, where would you guys look, the 5 or the 6? Probably the 5. just because we know we're still getting the 4 volts here, we know we're getting 4 volts out, this stage should be upping it to 5 volts. And so lo and behold, we look, we're getting 4 volts there. So we know that our problem is right here in between those two stages. It could simply be the output of this stage didn't get connected right into the input of this stage. Like on your breadboard. You missed the row by 1 on the output. It happens. But the whole idea is we have this whole complex system, so now we can look at here, we had to take 3 measurements, and now we have a very good idea of where our problem is. Now we go back through, let's say we go in and we find that, yes, this was mixed up. We fix that, we come back out, we look on our output. Now we're getting 8 volts. So what do? Yeah, we do it again. We troubleshoot this problem again. Only this time, I would say, let's, based on what we previously did, what's our problem? We could just check everything, but again, that's going to take time. Yeah. So again, we're going to half split it again. We're going to check all the different stages. 4, 5, 6, 7, 8. So when we half split it, do you think it's probably safe to assume that these ones are correct? Yes. So we're fairly confident the problem's not on that side. So without even having to take a measurement, based on our previous measurements, that side's good. So now we've got these ones. We'll split it again. So this is 5, 6, 7, and 8. Where do we think our problem is going to be this time? Probably the 7 and 8. So right off the bat, we can eliminate another 2 just by using by half splitting and by using with what we had before. So again, our problem is probably right there. It's either the stage 8 itself, or there's a problem between these two stages. So even with this, we can have problems. So we go in there and we find out, yep, between 7 and 8, again, I missed my outputs by 1 row on our breadboard. I moved that wire, connected improperly, and now my whole circuit moves away. Now I've got 1 volt and 9 volts. But this way, if you notice, we had to do a series of, 3 measurements, and then some deductive reasoning here. And then we took a 4th measurement and found that, yes, that's where the problem was. Whereas, we could have gone through, started with stage 1, checked all the resistors in that circuit. Okay, they're good. Jump to step 2, check all the resistors and transistors and the capacitor in that circuit. Okay, they're good. Jump to step 3, step 4, step 5. Half splitting gives us the option to not have to spend so much time. And in industry, anytime you can save time is a big deal because that is money. Especially if you have multiple pieces of equipment that are down, you're one person. No matter how much you want to be or you try to be, you're only one person. You can only focus on one task at a time. Again, from my experiences, I had situations with this. I was the only one on shift. Everybody was sick or on vacation. And we had, I don't remember how many it was that night. We had probably 20 some odd pieces of equipment down. It was a mess. It was an absolute disaster. I was not looking forward to the morning meeting the next morning to explain why half the fab was down. But with this problem, I went through, and even with this, I was dissecting my list as far as what could I do that's going to have the biggest impact. So I looked, okay? I've kind of ranked my tools in order. I had a cluster of tools right in the middle that without them, nothing was going to get moved in the fab. So I went there and I used this half-splitting method just to determine which tool I was going to work on first. I sorted everything, figured it out, and I told, because my managers were on me, they were like, we need these tools. I'm like, I'm one dude. Like, let me see what all's down. Let me come back to you. Let's come to a consensus. I brought them this data where I basically showed everything based on the rank. And it was kind of a rank that I did, but from the experiences I'd had being an engineer, I knew which tools were important. I said, this is the cluster of tools I need to work on. They may not necessarily be the ones that have the most whip at the moment, which was work that we had, work in progress. But I told him, I said, if I don't get this fixed, nothing's going to be moving, even if I fix the outside ones. And so he's like, okay, I accept that. Go do it. And this cluster here in the center was the easiest fixes. They were just ones that had to go real quick, mess with some settings, reset the tool a little bit, get it back into a position it wanted, and then it took off and was running. Once I got that done, we met back and we're like, okay, where do we need to go from here? We got this centered cluster fixed. Which cluster do we want to go after next? And we use this exact same kind of troubleshooting method. You know, not even to fix the direct problem, but just to figure out what to fix, where best was to spend my time. And honestly, with that, I actually got some praise from this from my bosses because there was so much down. And I actually was able to document that because there was still a lot down in the morning. But I said, this is what we were doing. This is what I tried to do to make sure we kept things moving. They were actually impressed that I had the foresight to think about that and not just, you know, pick something at random. So this is something that you guys are going to be using throughout all your careers. And then anytime you build something, it's not going to work right the first time. I can almost guarantee that. If it does, celebrate it and wait for something to break. Because it's going to happen. But just know that, you know, even though something does go wrong, you guys can do this, okay? Half split your system. Figure out, at this point, I should be having this. If I'm not, is my problem before or after this point in my circuit? So same with your resistors. If you're getting values that you think are kind of weird, start looking back. Start half splitting your circuit. Is this resistor okay? Is this point okay? Can I work backwards from here and make an educated decision? This is just one method, but it's one that you'll use a lot. Okay. The last terminology that we have, and then we will go to break, is one more Kirchhoff law. Kirchhoff's current law. So Kirchhoff's voltage law still reigns supreme. It still applies, but it has a bigger direct impact and influence on series circuits. In parallel circuits, we are a lot more concerned with current flow than we are with voltages. And we'll get into that a little bit later, I think tomorrow. We're going to do some of the supporting math first. But Kirchhoff's current law is current going into a node must equal the current leaving. So Kirchhoff's current law, current going into a node must equal current leaving. I apologize for just writing in symbols. It's faster. My handwriting is terrible. And this way at least we can understand. There, I like that a little bit better. Which basically means if we have a connection point, and this even works with a series circuit. So I have this circuit. I have current coming this direction. And a node, and you'll see it on schematics, if there's a dot, there's a node, which basically means these two or these multiple things are physically connected together. There is a path for electrons to follow. If you see wires that look like this with no dot, they don't connect. Because sometimes on schematics, you don't have a choice, but you have to cross those wires. So when you do cross them, you should have a dot to indicate that there is a connection. So this is a node. This is no node. This is the node. Just so you don't get confused, because like I said, there are times, especially when you get into digital and you're dealing with computer chips, in your schematic, you're gonna, no matter how hard you route them, you're gonna have a chance where they could overlap. So you either do this or you do this. You don't put a dot or we put a little bridge. So then the idea here is the current going into a node must be equal to the current leaving. So in a series circuit, if we have 1 amp of current coming into this node, going down through this resistor, how much current is going this direction? 1 amp. because this has to be satisfied. Current going in has to be current leaving. If this were the case, this connection, let's say we had 1 amp, we had 2 amps, and we had 3 amps. How much has to leave? 6 amps. This is the guiding principle of parallel circuits. The current going into the node has to equal current leaving. If it doesn't, we've calculated something wrong. Or we have extra power coming in that we shouldn't be, or so things like that. So just like with Kirchhoff's voltage law, so in a loop, all the voltages have to equal 0. The current, basically the currents have to equal 0. Your inputs have to equal your outputs. That also goes along with the conservation of energy. We cannot create energy. We cannot create matter. What's there is there. We can't lose it. Just because we may lose it in our measurements doesn't mean it's not really gone. We've missed it somewhere. Okay, so really that's all the terminology we have for right now. So let's go ahead, let's go to break, and then when we come back, we'll launch into some of the supporting math for this section.